Okay, we're going to go live. Going live. Okay, we did it. We went live.
We're usually in the middle of some rolling conversation at this point.
I know. Yeah. Yeah. Usually it's like we're talking. I'm like, we're live, by the way.
Yeah.
Yeah. We're live, by the way.
Great.
Yeah, so buckle up, everybody. Tonight's, as Nancy just posted in the chat, tonight's interview is epic. Normally I try to aim for like a 15 to 20-minute interview, and 25 minutes in today's interview, I just threw up my hands and just said, I just rolled over, showed my belly, and just gave up.
Can't wait to see it.
Yeah.
I like my dissertation.
Yeah, is that? So explain this to me then, Brian. He was your PhD advisor.
Yes, he was my PhD advisor at the University of Connecticut.
Wow.
I did my PhD on radiating black holes in the early universe. So dynamic black hole systems in the early universe.
That is amazing. And so you had to run his gauntlet?
Yes.
Did you live stream the whole thing like Moya did, or no?
No, we didn't have that. But the thing is that the thing about Ron Mallett is that in class, he's very gentle and kind and informative, and then when he becomes your advisor, he expects a lot.
Yeah, that's awesome. That's good though. I mean, I think that's what you want, right? In an advisor, ideally. Yeah, you want them to push you.
Yeah, it was definitely. I think I got 4 papers out of it.
Does Kipping push you guys, Alex? Is he just too nice?
Well, he's very nice. I wouldn't say he's pushy. I mean, he is just such a research beast. I mean, he can like knock out a paper in a weekend sometimes. He has an idea on Friday, and by Monday he's got like a draft. And that's, just try to hold on,
try to keep up
with that,
Yeah.
Just new ideas coming at you all the time. And, you just pop into your office and you're working on something. It's like, oh yeah, like have this idea. And then you just kind of go off in this whole other direction. So it's fast paced, but not because it's really like, pushing you so
right.
hard. I mean,
he's not a jerk about it. He just sets a brutal pace and you want to try to keep up.
Yeah, and you really can't keep up. You just do your best.
Yeah. No, but that's good. That's really inspiring, I think, to be able to work with somebody who can turn a rough idea into a concrete paper in a short period of time and have it be coherent, and it almost seem effortless.
It's really astonishing.
Yeah. When I was learning to write like 20 years ago, my mentor, he would write a novel every 6 weeks or so, and he would write and he was doing a lot of work for like the role-playing game industry, and so he would write books for Dungeons and Dragons and for various other properties, and he would, you would request, say, a source book. It would take him 2 weeks. If you wanted an adventure, it'd take him 1 week, and he would just fill his calendar, and he just said the trick is to write fast first, and then you will learn to write well by learning to write fast. And that always stuck with me. And so my first instinct is always just to write fast, and then if I have more time, I'll make it better. But it's great to work with people that sort of have that kind of hustle mindset. Yeah, totally.
Sure.
Yeah. Okay.
Yeah. So sorry, just finish the thought. Kipping doesn't really have a rushed attitude. I mean, he like knocks stuff out, but it doesn't feel like he's go.
Yeah, no. Just to work on something cool. Yeah, no. So like I said, my mentor, he would just every day his goal was 5,000 words every day. So he would just sit down at the desk beginning of the day, and he would write 5,000 words, and then he would be, whenever he hit 5,000 words, that was the end of his day. And it could be within 4 hours, 5 hours, or, might take him the full 8 hours. And he just treated it like a job. Just this idea of turning pro. And so that set my expectations, my standards for what it was about to write. Was like a writer sits at their desk at 9 a.m. with their coffee in hand, starts writing, takes lunch, keeps writing, 4 o'clock goes for beer. That's
yeah, sounds nice.
Yeah. And so it's good. And so even now, like if I have to write anything, if I have to write a script for a video or whatever, right? I don't obsess about it. I just get cracking. All right. Let's get into the show. All right. Put you guys all back in your boxes. There's me. There's my intro. All right. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, May 5th, 2021. Cinco de Mayo. So this week we are going to be talking about a really good measurement of dark energy. China launches the core module of its space station, and of course, the dramatic, successful, non-explosive launch and landing of Starship SN15. Joining me this week, I got Alex Tichy. Hey, Alex.
Hey, Fraser. How you doing?
Hold on. There you are. Okay, good. And we've got Dr. Brian Coberline. Brian.
Hello, Fraser. It's good to be back again.
Good to have you back. So before we get into this week's episode, I just want to give a huge thank you, of course, to our good friends, fans, executive producers at the Weekly Space Hangout crew. If you want to be a member of this amazing community, go to wshcrew.space, and they will give you your credentials so that you are an executive producer. So once again, wshcrew.space. Special thanks to everybody there, especially our producer, Nancy Graziano. All right. Brian, you're on my screen right now. Tell me about the... actually, you know what? Before we get to Brian, I just got to sort of explain what's going on here. We've got an epic interview with Ron... Is it Mallett? Ron Mallett? And it's like 45 minutes long, but I promise you it is terrific. So we're going to catch up on the news with Brian and Alex first, and then we'll shift into the interview at like the 20-minute mark, and then just go on with the rest of the episode. So, but I promise you're going to love it. It was one of my favorite interviews that I've ever done, and I think you're really going to enjoy it as well. I kind of just was along for the ride, but I think you'll really like it. Okay, Brian, tell me about dark energy.
So the basic idea of dark energy is that it's what's causing the universe not just to expand, but to expand at an ever accelerating rate. And we've known about it for quite a while, the study that won the Nobel Prize. But the thing is pinning it down. Like what we don't know is we don't know what dark energy is. It could be something like a cosmological constant, some structure within space and time itself. And if that were the case, then it should be expanding the same everywhere. And if it's some fifth fundamental force or something like that, then maybe it expands in different directions at different rates. We still haven't figured that out. And so one of the things we really want to have is really good measurements of what cosmic expansion is, which is a measurement of dark energy. And what's cool is there's this process where you can do it that's called baryon acoustic oscillation, which is a fancy name for matter gravitationally clusters galaxies together, and dark energy tries to pull them apart. And so if you have both of those working together, what happens is clusters of galaxies tend to cluster tighter, and they form nice little pockets. And the dark energy tends to spread everything apart. And so you have these voids in between these clusters. So you have clusters and voids, and you may have seen these pictures where there's little cluster things and filaments and big empty gaps. Well, it turns out that the amount of dark energy we have in the universe will determine the scale at which that clustering happens. So if they cluster really close together, there's not a lot of dark energy. If the voids are larger, there's more dark energy. It's a little bit more complicated than that, but that's basically the idea. So what you can do is you can do a survey of where galaxies are. So where are they in the sky? How far away are they? And map out the clusters of these galaxies. And when you do that, you can get a measurement to pin down how much dark energy there is. So we've done this before. There's the thing called the Baryon Oscillation Spectroscopic Survey, or BOSS, that mapped out, for billions of light years, where these galaxies are. And that gave us a good measurement of what dark energy is. So one of the challenges is that when you measure how far these galaxies are, because you're looking at such large distances, you're using a thing of redshift. So basically, as the universe expands, light coming from a galaxy is stretched, it's redshifted. And so the more redshift it is, the more it's been stretched between us and that galaxy, and therefore the farther away it should be. So that's all perfectly fine if they were all standing still. They're not standing still. So these galaxies, because they're clustering together, they may be moving in different directions. And that relative motion to us also causes a redshift or a blue shift. So you've got the cosmic redshift, and then you've got all of these little galaxies moving that are also redshifting. So this new study that was the extended BOSS, so the extended Baryon Oscillation Spectroscopic Survey, looked at two things. It looked at the baryon acoustic oscillation, the clustering, but it also looked at a statistical measure of how galaxies deflected from that. So what they call a redshift space distortion, which is the statistical deviation from the overall whole. What's nice about that is that what you can do is when you apply that, it gets rid of a lot of the kind of systematic errors. So if you had these super clusters that are all kind of going one direction, well, that would make it more redshifted than it should be. And that would skew all of your data in the measure of dark energy. So by applying the statistical method, you could actually kind of recalibrate everything and narrow down the value of dark energy. So in this latest study, when they did this, they found the measure of dark energy, but they did it to a precision that was 11 sigma. So this is, I went on my calculator to try and calculate 11 sigma, and it doesn't even work.
Well, I mean, when I think about like people getting really excited, I mean, we were talking about the recent, the muon G-2 experiment, and they were really 4.2, sigma 4.2 detection was like 1 in 100,000 chance that it's wrong, right? And a 6 sigma is like a 1 in 10 million chance. I forget, the 1 in a million chance that it's wrong. So 6
sigma is typically what we'd say, yeah, that's certainty, that's proof.
Right. And so 11 sigma.
So 11 sigma is so far out on the bell curve.
Right, that's just showing off.
So way out there.
Yeah.
It is about as certain as you can get. I mean, at that point, it gets so, the differences, I think, become so tiny that you're talking about, scales of trillions of years or anything like that. It's like, it's not going to happen.
So what did they discover with this measurement?
So the initial one was just confirming the value of dark energy that they did to a really high precision. So that's kind of, in some sense, this study is boring. Yay, dark energy exists. We've confirmed it again. But the exciting part is that they've confirmed it so accurately that you can really start looking at how the variations might skew that. So if you have that level of accuracy, then you can say, okay, is it really uniform in all directions?
Mm-hmm. Okay.
Is it uniform over time?
Mm-hmm.
So you can say, because if it's a cosmological constant, it has to have a fixed value everywhere because it's just a part of the fabric of space and time. But if it's something else, if it's a fifth, fourth, if it's quintessence, if it's some field vacuum thing, whatever, then you could have time variation, you can have spatial variation. And so what this really does is this kind of sets the groundwork for pinning down what dark energy is. And
so, when you talked about those like space variations, so in other words, that if you look in one direction and there's more dark energy than in the other direction, then it might just be dust, right? Because you're seeing the dust of the Milky Way, or who knows what it is. But
except that matter would behave in a different way.
It can always be dust. Don't. don't don't tell me that you're certain that it's not dust, because it is always dust. But I guess, this idea of the time variation, that's really interesting, because there's sort of two big questions, right? One being this crisis in cosmology, this idea that you've got these different measurements of the expansion rate of the universe early on in the universe, and then also later on in the universe, and a change in dark energy would handily explain why you've got a different expansion rate in between the two zones. So in theory, I'm assuming you could then go at 1 billion years, this is how much dark energy was present, and at 2 billion years. And then, of course, that other question that is more existential is the universe going to tear itself apart in the future? Is dark energy increasing and we're going to see a big rip? Do we have answers to either of those questions? No. Wait a minute. 11 sigma and you can't tell if there's a big rip? Come on. Like,
I can give you the boring answer with perfect precision.
So when do we learn if there's a big rip?
This is one of those things that you have to be careful taking a linear extension and assuming it's exponential. This idea that it's just going to constantly expand at an ever increasing rate, no matter what, down to the scale of atoms. We don't know that. We don't know the nature of dark energy. So we can't say that is what's going to happen. Is it a cool idea? Sure. But do we have evidence to confirm that it's a valid theory? No.
I feel like what do you want? 12 sigma? Like at what point? I don't know. I just feel like we're waiting for that answer to know if the universe is going to tear itself apart. I got to know whether we've got 10 billion years left or 10 to the power of 100. Which is it? Because
you know why the universe slowed down.
Yeah, I need to plan accordingly depending on which one it is.
You can plan accordingly. If you live your life as if the great big rip is going to happen, everything will be fine.
Okay, all right. Awesome. All right, Alex, China launched their space station.
Yeah, they sure did. This is kind of what I think is the most exciting development of the last week, just on last Thursday, I think. So just after last week's show. New space station called Tianhe, and it's they've launched it on this Long March 5B. This is their heaviest lift rocket. It's comparable to Delta IV Heavy and Falcon Heavy. It's the third most powerful rocket in the world right now. And, this is sort of the third iteration. They've had these sort of space laboratories back in 2011 and 2016. And so this is going to be their big one. It's the core module. They're going to add several modules onto this, and it's going to be really comparable to Mir when it's
it really looks like Mir when you see the illustration of what the final product is going to look like.
Right. Yeah. So smaller than ISS, obviously, but comparable to Mir. Which I'm old enough to remember. And I think that we deorbited in 98, I think. So it's been a while now. But, of course, famously, China is locked out of cooperation with NASA and it has no participation in ISS whatsoever. And so they have to go it alone. They've had cooperation with Russia over the years. And so, if you look at their crewed spacecraft, it looks very much like the Soyuz spacecraft. So there is some sort of information sharing there, but basically they've been doing their own thing, and they're just being super successful now with both their crewed space program and obviously their moon missions, the Chang'e series. They had a sample return not long ago, and when it comes to this particular missions, they've already got 4 missions planned for the rest of this year, both cargo and crew. It's going to hold 3 astronauts, or taikonauts, sometimes they're called, the Chinese astronauts, and then 5 or 6 missions scheduled next year. So this is really just sort of amazing. They are locked out of working with NASA because of, it's federal law that they can't cooperate. The idea is, that they don't want sharing of this sort of information for ballistic missiles and that kind of thing. But they're really holding their own. I think it's an interesting question as to whether or not that policy should be reversed. obviously, the United States and the Soviet Union and subsequently Russia, we have all these sort of political, conflicts between these two superpowers. And obviously there are conflicts now between the United States and China. But, if we look at the space program, that's been one of sort of the rare examples where we really were able to cooperate even with someone who's otherwise somewhat adversarial nature. And so, I think it'd be interesting to see if in the future there can be some cooperation again between the Chinese and American space programs. China, for their part, seems to be willing to, kind of join the international fold. It's really on the U.S. side that's being restricted right now, but we'll see what happens in the future.
Yeah, I mean, it's always best when these countries can actually work together and collaborate. And I think one of the real victories in diplomacy was getting the partnership between the Russians and the Americans for the International Space Station. I mean, it was whatever was happening, you knew that they were up there depending on each other in space, working as a team, fostering goodwill, and I think that it created a lot of political sort of peace, and I would love to see the same thing, because I really would hate it to turn into this race against China to have people on the moon, for it to be a fear-based thing that's moving forward. It would be great if it was that they were bringing their capabilities to the table and helping to push space exploration. I mean, that was sort of the hope with the samples, and they have offered, and they're letting various people work with the FAST instrument in China. So, right, yeah, it will be that's the hope,
competition right? Competition has had its value, obviously, in the space program. Racing to the moon, for example, is not entirely a bad thing, but whenever we can cooperate, I think it's valuable to find those opportunities. You think about the political situation more broadly between the United States and China, and something like climate change. Again, it doesn't always have to be adversarial, and there's those moments where we can find cooperation. Real quick, sort of the other big story about this is this Long March 5B is coming down for an uncontrolled deorbit. So not everything has gone entirely smoothly. Ordinarily, we want to control where these spacecraft come down, and this is a big rocket, like I say, it's third heaviest lift in the world, and so a rocket of this size, pieces of it are going to burn up, but pieces of it will definitely hit the surface. Seems like somewhere around May 8th or May 9th, and they don't know exactly where it's going to come down. I mean, they know its flight path, obviously, but these uncertainties mean it could really come down anywhere along its orbit, and chances are, of course, that it will land in the ocean somewhere. But this is something that people are really looking at right now, and tracking this. It's losing a few tens of kilometers every single day, and so it will come down in the next few days. Yeah,
we saw that with the Tiangongs as well. They deorbited, and the same situation, and it's going to be tricky. I hope they've got better deorbiting capability when the station itself actually comes back in.
Yeah, sure.
All right, so just before we get on to the interview, just one last little piece of news, and of course, just like an hour and a half before we started this show, we saw finally SpaceX was able to launch and land one of the Starship prototypes. This time it was SN15, so it took off, went to its appropriate altitude, flipped over onto its side, did its belly flop maneuver, fell back down, reignited the 3 engines, and did a beautiful landing burn, landed successfully on the launch pad, caught on fire. They put out the fire, we think. And so we're now an hour and a half since the actual launch and landing, and it hasn't exploded yet, although maybe somebody in the chat will tell me that it has exploded. So far, cross our fingers, they're going to be able to use this prototype and launch it again. Pretty exciting. And with SN15, they made a pile of improvements, both to the engines as well as the rocket itself. I think this is the one that has, I think they made like 100 improvements overall that they implemented simultaneously on one version update, which is a terrifying thing to think about. And people are mentioning in the chat that there's a bunch of things. SpaceX's birthday, there was a ton. It was it's the anniversary of the first American in space. So it's a good day. Congratulations, everyone at SpaceX. Now go to orbit. That's the trick. All right, so we're out of time because, again, a gigantic interview. So we're just going to quickly. I'm going to let my co-hosts hit the road and enjoy the rest of their evening. So, Alex, you're on my screen right now. What are you working on, and where can people find out more?
These days, I'm building out my code. I've got a code called MoonPy. That's your one-stop shopping for downloading and detrending and manipulating and visualizing light curves from Kepler and TESS. And it's just all kinds of bug fixes. That's what I'm working on these days.
Did you ever know you'd be a coder? Did you ever know that would be your future?
Well, that's the job of astronomers. But I didn't know that I would like it so much. It's really my favorite part of the job favorite part of the job is coding. I do love to code. So I do it every chance I get. It's almost like procrastinating by coding sometimes. But if you want to follow me on Twitter, it's just my name @AlexDG.
Awesome. Brian, what are you working on?
I'm working on an article for University Today in the next couple of days. And as for where you can find me under my name on Twitter, so @BrianCoverline or BrianCoverline.com, which is my website.
Perfect. All right, so I've got an interview coming up tomorrow with Dr. Brendan Dick. He's a geologist at the University of British Columbia and has done a new study on exoplanet habitability and sort of new ideas about how the geology of the planet will affect the habitability. And that's like tomorrow morning at 9. I've got probably a couple of other interviews coming up this week as well on my YouTube channel. So stick around for that. All right. I'm going to bring my co-host back on screen, going to wish them well. And last time I did the pre-recorded interview, I forgot to sort of do my big spiel and thank you. It's sort of a cold cut at the end. So thank you, guys, for joining me on this very quick episode. Thanks, everyone watching us both on YouTube and Twitch. And a special thanks, of course, to Nancy Graziano and the rest of the Weekly Space Hangout crew for keeping us organized. All right, guys, we'll see you later. I'm going to move into the interview portion of this week's episode, and buckle up. It's a good one.
All right. See you.
Thanks, everybody. All right. Here we go. All right, our guest today, Dr. Ronald Mallett. Welcome to the Weekly Space Hangout.
Oh, thank you. It's a pleasure for me to be here.
So the question I always ask people, who are you? What do you do?
Well, I'm a theoretical physicist at the University of Connecticut, and I'm Professor Emeritus and a research professor there. And that is my specialty is Einstein's theories of relativity, things like black holes, the Big Bang theory of the universe. And also time travel, which is part of Einstein's theories. But that's my job.
Well, we'll definitely get into the time travel part in a second, but how do you feel about how well Einstein's theories of relativity have held up to all of the tests? It's funny, we're always writing, Einstein, still right after all these years.
Yeah, well, the thing is I think that when it comes to the special theory of relativity, that question isn't asked anymore because it's so much a part of our everyday life that it's like in the background. Although people don't realize that, but it's the general theory of relativity that actually that question goes, because that was his theory of gravity. And there's still things that we don't understand about gravity. One of the most important of them is how do we bring it together with quantum mechanics? That is really one of the frontier problems, is joining general relativity with quantum mechanics. And whenever we've come up with new tests, for example, the verification of gravitational waves. The Nobel Prize in 2017 was won for that discovery, although that was something that Einstein predicted over 100 years ago. And the observation was because when you have two black holes colliding, it causes these ripples in space, and that was a prediction also. And the thing is that so this actually verified that. We had indirect evidence of that, but this was actually the first direct evidence of that. So we have to keep testing it because there are many aspects of it that just haven't been tested yet.
And it is funny, though, because, as I said, we were continuously writing these articles that another test of Einstein's has finally been experimentally proven, 100 years after, in ways that I'm sure he never even would have thought
Yeah, that's true.
It's just incredible.
Yeah. Well, but that also brings back an extremely important point, because it's sometimes overlooked by people that science and technology go hand in hand. And scientific discoveries, in fact, the early discoveries, even in terms of quantum mechanics, people don't realize that quantum mechanics actually owes its birth to trying to come up with a better light bulb. And I'm serious.
Yeah.
And that was a technological thing. Okay. Yeah. And literally that's the root of it. Although people they jump into what it is, but that was actually root. And so the thing is that in order to science requires technology in order to test things. So there was not the technology around to demonstrate Einstein's theories at that particular point. The other aspect of it is people have no idea whatsoever of how expensive these experiments are. Remember the one I just mentioned about colliding black holes and ripples in space? How expensive could that be? That cost $1 billion, $100 billion. When I tell people that, their mouth drops open, because the thing is they say, how can that be? And that's the other aspect. So it's the technology plus the cost.
Right. And so one of the implications of general relativity, you feel, has a possibility for time travel. So can you talk about that?
Oh, yeah. In fact, now, one thing I should point out is that his special theory of relativity, which came out in 1905, it's important to understand why the general theory of relativity came about at all, because, people would say, well, why did he even go there? The thing is that the special theory of relativity showed in a nutshell that time is affected by speed. Time for a moving clock slows down. The faster a clock moves, the more time slows down. And there's been many, many, many experiments now that have demonstrated that, okay? The thing is that, however, the basis of the special theory of relativity is the speed of light. And according to Einstein, no signal should be able to travel faster than the speed of light. That's actually a bedrock of the special theory of relativity. And what Einstein's special theory of relativity did, it was looking at the other thing is it looked at objects in constant motion, where the velocity doesn't change. That was another portion of it, okay? So those are two things. One, that the speed of light is a constant, and that is the limit.
Yeah.
And also the other aspect, as I said, is that it did for motion that was to constant velocity. Now, Einstein wanted to apply the special theory to every single aspect of physics, and he did. Electromagnetism, in a sense, was already part of it. But when he came to gravity, that was a problem. And that's something that should be understood, because what it predicted, Newton's theory, in a sense, predicted that it violated special theory of relativity. What do I mean by that? Well, one of the classic examples I think that I like is the fact that, that the Earth is 93 million miles away from the sun. And that it takes light 8 minutes to travel that distance at 186,000 miles per second, okay? And what would happen if there was a cosmic catastrophe that would destroy the sun? What would we see? Now, that's not rhetorical. What would we see? Because the thing is according to Newton, gravity shuts down immediately. So would have the following weird situation. The sun is destroyed, so there's nothing to keep us in orbit. So we would fly off in a tangent into space. However, we would still see the sun sitting out there in the sky, because it would take 8 minutes for that to go. So according to Newton, that was a contradiction with Einstein's theory, because according to Einstein, it takes a finite amount of time for light to get to us, but gravity instantaneously shuts down. Einstein said that cannot be so. And so literally the reason for him developing the general theory of relativity was to bring gravity.
Right.
In. That was the root. And that's an important aspect.
Yeah, and I mean, speaking of tests, right, it really wasn't until the kilonova event just in 2017 where we saw the gravitational waves and the radiation arrive at essentially the same time that we finally got this beautiful test that they were truly moving at the speed of light.
Exactly. In fact, that's exactly right. And the thing is that, but that was the reason why he developed the general theory of relativity in the first place. Now, the other thing that is important in order to understand how time fits into this is to understand what he had to do to get gravity to obey that law. Okay, what he had to do was, he said, gravity is really not a force. Gravity is actually a property of space. And what did he mean by that? Well, one of my favorite examples is the fact that, and I use this sometimes whenever I'm giving talks, is imagine that you had a rubber sheet, say a small trampoline, okay? And suppose that you put a bowling ball on that sheet. It curves the sheet. Suppose you take a marble and set it on there. The marble moves down to the bowling ball. Now imagine that that sheet is there, but it's transparent now. So all you can see is the bowling ball and the marble. Now, from that standpoint, when I drop the marble and it moves towards it, you would say, oh, somehow the bowling ball is pulling on it. But that's not what's happening. You know what's happening is that the bowling ball is curving. And in fact, one of the things you can do is, if you get that marble a little sideways motion, you can actually get it to orbit around. But you know, once again, that what's happening is that it's orbiting that curved sheet. Well, Einstein said, that's an analogy, but Einstein said that what the sun is doing is the sun is actually curving the empty space around it. And that what happens is that the Earth is actually moving in that curved empty space. We can't see it, but it's there. So according to Einstein, gravity is not a force, it's actually a curve of space. Now, this is important because sometimes popularizers get it wrong. Gravity doesn't cause the curvature of space. Gravity is the curvature of space. That sounds like a small semantic thing, but it's actually key. Gravity doesn't cause the curving of space. Gravity is the curvature of space. Now, the thing is that in addition to that, Einstein's theory, space and time rejoined each other at the hip. It's called space-time, in fact. Whatever you do to space also happens to time. In a special theory of relativity, what that means is that when you speed up an object through space, it also causes a dilation of time, slowing down of time. In the general theory, what that shows up is that whenever space is curved, there's a bending of time. And what does a bending of time mean? That shows up to us as clocks slowing down. So according to Einstein, for example, our Earth is curving the space around it. So according to Einstein, when you get closer to that curve, which is closer to the surface of the Earth, clocks should be running slower than they're running at a high altitude. Now, one thing that I've found is that a lot of people, even people who have the background, sometimes aren't aware that that test actually occurred quite a while ago in terms of the GPS. Just to remind you, the GPS system, the way in which it works is that right now we have these satellites above us that are sending a signal at a certain time that reaches the unit at a certain time, okay? And the thing is that you know that if you know the time the signal was sent and you know the speed of the signal, you can compute distance, okay? And the thing is that when they were setting up the system initially, they were getting incorrect distances. And the reason why is they were assuming Newton's theory of time. According to Newton, nothing can affect time. Speed, gravity, nothing. And so when they were setting up the clock, this really was happening. They were assuming that the clocks aboard the satellites were ticking at the same rate as the clock in your unit. And when that wasn't happening, what they did was the physicists said, look, you have to take Einstein's general theory of relativity account, because the clock in your unit, your GPS unit, is actually, because it's close to the Earth, is running a little slower than the clocks on board those satellites. Those clocks are actually running faster than the clock. And they use computers to actually take that into account. So you might say that was that was a major initial test that gravity does affect time, okay, was that. Now, here's the other thing though, and this is where now the thing is that this means that the stronger gravity is, the more time slows down, that actually has the same effect as speed on time, okay? And in fact, what that means is that, for instance, you know that the black hole is probably the most intense gravitational field that there is. And the prediction is that if you get close to a black hole, the closer you get to a black hole, the more time slows down. And that actually is something that we know would happen simply because of the fact that we see the slowing down of time here on the Earth. I should mention that one movie that I really like that gets it right, and that's Interstellar.
Yeah, that's the example I always use as well.
They did a great job in that. Okay.
Yeah.
But now here's the point. That means that a black hole can allow time travel to the future.
Yes.
Just like, this, if you speed an object up. However, there's something else that happens in Einstein's theory, which in Newton's theory, we have just that. Okay. I mean, you can't do anything with time according to gravity. But here's the other thing. Remember, I said that gravity is a property of space. You can think of it as a fabric, but now you can actually think of it even more malleable. Suppose that you have a rotating object like the Earth or a rotating black hole. Then that means that not only can you get a bending of space, but you can get a twisting of space. Okay. What would that mean? That would mean that, for example, if you had something out in space, like for instance, gyroscopes, say in a polar orbit, with the Earth rotating under it, that polar orbit should actually twist. Okay, that should be happening. Now, the thing is that there was, in fact, a very, very important experiment that was done that actually demonstrated that, okay, called Gravity Probe B. Gravity Probe B actually showed that gyroscopes actually shifted because of the rotation of the Earth. Now, here's an interesting thing that comes up even in addition to that. So that was a whole new prediction, and that's actually been demonstrated. But now, if the rotation is strong enough, for example, let's suppose we're talking about a rotating black hole, then that twisting becomes extremely strong. Mm-hmm. So in addition to bending time, you actually get a twisting of time. Now, normally, and this is where time travel can come, because normally for all of us throughout our entire life, we move along a timeline.
Right.
You can think of it as, think of taking a strip of paper and drawing a timeline on it. And at the bottom of that line, let's say you put the past. At the middle of that line, you put the present. And at the top of that line, you put the future. All of us throughout our life live along this line, okay? However, once again, space-time are connected to each other. If I have an object rotating rapidly enough, it can cause an extreme twisting of space, and that extreme twisting of space, because time is embedded in space, causes a bending of time. So imagine now that I'm rotating the space and I twist this time into a loop.
Right. I'm sort of imagining like a procession of time. I can't even sort of imagine what that means, but just think of, as I said, literally a good analogy is just think of the fact that I'm just taking, here I'm twisting space, and I'm going to twist this strip of paper into a loop. Right.
Now look what I can do. I can start out at the past and move along the strip of paper to the present and move along and continue to the future. But what I've done is I've made time into a loop. Right. So I can go from the future to where? To the past. So what that means is that by twisting space, I can twist time into a loop, and I can create a loop in time. This would allow me to travel into the past. In the special theory of relativity, there's no way that you can travel to the past. That's it. There's no way. No matter how fast you go, right, you can't get to the past. But in general theory of relativity, because of the fact that you might say gravity is this malleable property of space, we can bend space and we can twist space. And so this means that a rotating black hole, which is you might say the extreme twisting of space, it can cause a twisting of time. And the calculations, the mathematical calculations actually show that if you go to, in a proper way, towards, now, and this is important because we have to distinguish between non-rotating and rotating black holes. In a non-rotating black hole, if I go into it, I'm history.
Yeah.
Okay. But it turns out that there's a special property for rapidly rotating black holes. If they're rotating, there's an angle that you could go into and you can actually come out again.
And in this case, you're actually, are you crossing the event horizon, or are you just getting close enough?
That's because there's enough different. There's with rotating you might say, this is a good point. It's a subtle point, but with non-rotating black holes, there's only one horizon. It's the event horizon.
Right.
And once you cross that event horizon, that's it. However, for a rotating black hole, there's actually two horizons.
Right, of course.
There's an inner event horizon, and that's why I said you have to go at the right angle. There's an inner event horizon that if you go into that one, you're done.
Yeah.
But there's an outer horizon that if you go through that, you can go into and out of the rotating black hole and end up in the past.
Because the time is twisted so much.
Right, you got it.
Yeah.
Okay. That has been shown mathematically. We haven't demonstrated it experimentally, but that is actually a part of the property of a rotating black hole.
And so, sorry, just to sort of labor on this for a second. So theoretically, then, I guess, however close you get in your angle of attack, the farther you're able to go back in time, like the closer you get to the inner event horizon, the more of a dramatic shift that is. Would the limit be when the black hole first formed, when it first started to rotate?
In fact, that's a very, very good point, because it brings up another point that people sometimes forget. This loop that occurs because of the rotating black hole. Before the rotating black hole was created, there is no loop. Mm-hmm. That means that you could go back into the past. Let's suppose we found a rotating black hole. And let's say the rotating black hole was formed, let's say, 1 billion years ago. Okay, that means that you could actually travel back in time 1 billion years up to the point that the rotating black hole was created, but not beyond that, because sometimes people think that when you have a time machine, and a rotating black hole is a kind of a time machine, that you can go back to any period. You can only go back to the point when the device was created. And this happens even for wormholes. Mm-hmm. You cannot go back in the past earlier than when the wormhole was formed. And with my work, it's the same thing. My work is based on Einstein's general theory of relativity. Right. So it has that limitation. Now, people have sometimes fantasized, well, will there ever be a way that we could get, let's suppose, for the fun of it, that, and now actually we know now scientifically, due to the fact that there are a great number of these what are called extrasolar planets, we know that eventually there will be an extrasolar planet. In fact, physicists even have a name for it. Some of the planets are too close, they're too hot. Some of the planets are too far away from their sun, they're too cold. But there's this class of planets that are just right. They're called Goldilocks planets. And these Goldilocks planets should be able to, some of them, have water, have life on them. Now, suppose that there are civilizations out there, which very likely there might be, that have mastered time travel and have created their device, let's say 10,000 years ago. Well, the thing is that we don't have a machine right now, but if we were able to find them, we could use their machine to actually visit our ancient past.
Yeah.
Okay. So that is one way we could actually overcome this limit.
Yeah.
To be able to go back to our past. But as I said, right now, we haven't created a machine that'll allow us to go back to the past yet.
Right. And of course, I mean, practically speaking, you've got horrendous tidal forces getting extremely close to a black hole. It's no picnic to do that. So do you have ideas on how this process could be tamed in a more reasonable level? Something here on Earth?
My work has been to show that there are other ways that it can be done. Okay. That has been my particular interest, because there's a key, and this is now we're coming back. Now we're coming to my work. Okay. I should say, we'll come back to that, but there's a very personal reason why I was interested in this notion of time travel to the past, but I'll mention that in a bit. The thing is that there's an aspect of Einstein's theory that is very, very different from Newton's theory. In Newton's theory, besides the fact of the curved space, the other aspect is that in Newton's theory, it's only matter that can create gravity. That means that, for instance, the Earth creates a gravitational field that keeps us anchored to it. The sun creates a gravitational field that keeps the Earth in orbit, and so on. Those aspects are similar in Einstein and Newton. However, in Einstein's theory, light is not matter. Light is just pure energy. But in Einstein's theory, light can create gravity too, just like matter. So now you can easily see what my reasoning was. If gravity can affect time and light can create gravity, then light can affect time.
Yep.
That's the core in which my research is based. And what I was looking at was a particular type of light, a special kind of light that was developed, actually part of Einstein's theory, by the way. Einstein actually looked at this property of light. It's called a laser. And a laser stands for, sometimes people forget that the name laser actually is an act, tells you what it is. It's light amplification by the emission of radiation, okay? And the thing is that that's important, because the thing is that light has this laser light in particular. Unlike other normal light sources which spread out, a light beam is like a pencil's beam. It's just like a straight beam. And what I did, I'm a theoretical physicist, I should mention. Okay, yeah. So this was not done by experiment. This was done by my solving Einstein's gravitational field equations, which was not a pick.
Yeah.
Okay. But what I did was I knew there was a device that really does exist called a ring laser. What is a ring laser? A ring laser, you can just think of it. Think of a square with mirrors at each corner. And suppose you send a beam of laser light from one mirror to the next mirror to the next mirror and to the next mirror. You could actually create a circulating beam of light. That's what I mean by a circulating beam of laser light. That device is called a ring laser. And it actually is a real technological device. In fact, there are gyroscopes that are based on that, ring laser gyroscopes. Now, what I did was I was working with analogies here, okay? And what I thought was that, well, wait a minute now, a circulating light beam, could that be something like, rotating matter? And if that's so, what I did was what I did with them was to sit down and solve Einstein's gravitational field equations for a circulating beam of light. And what I found in the solution was the fact that if you look at the empty space within that region, it turns out that, yes, it actually causes a twisting of space.
Right. And right? I guess you've got the advantage that it is going very quickly. And I guess E equals MC
as fast as it can go.
Yeah, E equals MC squared gives you the equivalent of mass that the however many photons you're dumping into your loop.
Yeah, and the thing is that you have to remember, though, that there's a little bit more, because that is part of the core. You're absolutely right. The fact is that you might say light has something like an equivalent mass because of the equivalence of matter and energy. But there's something about light which isn't like matter. In other words, if I have a ball, it sits there. There's no such thing as a photon sitting there. A photon is always on the move, okay? And so there's effects that occur for light that don't occur for matter. And in fact, if you have, let's say you take a lead rod, that would create a gravitational field. It would pull a particle towards it. But let's suppose that you just have a finite light beam going across, laser beam. It turns out that if you compute the strength of the gravitational field, let's suppose that it's the same length as the lead piece. It turns out that the gravitational field of the light beam is actually twice that.
Right.
Even though so it turns out that there's other aspects other aspects too. For instance, this is a really strange one that even some of my colleagues, who work have found it strange when they first encounter it. When you have, let's suppose you have two rods next to each other, metal rods, they will attract each other. Let's suppose you have two parallel light beams, they won't. Right?
Why not?
Well, the thing is that it's a technical term.
I mean, aren't they distorting? Aren't they both distorting space-time through their?
But they're not distorting it in exactly the same way.
Okay.
Okay, so they create gravitational field, but they're not. Okay, in Einstein's equation, there's a term, and I'll just throw out the technical. It's called the Ricci tensor. Okay, this Ricci tensor for matter is not zero. The Ricci tensor for light is zero.
Okay.
So if you wanted to go back to the mathematical root, that is the root, okay? This term called the Ricci tensor for matter is not zero. For light, it is zero. And that has a lot of other consequences. So that's why I said that sometimes when people talk about the equivalence of matter and energy, equivalence does not mean identical.
Mm-hmm.
And in this particular case, the properties of light and the way it bends space is not exactly the same way as the way matter bends space.
So I'm envisioning some kind of laser beam that is in a compacted area that is moving in some kind of circular fashion, you know, based on the mathematics that you put into this. Practically speaking, you know, how much laser, how small area, what do you
that's a good question.
What do you think it's sort of turning into?
There's two different things that are occurring here. Remember I said that you're getting a twisting of space that occurs. It turns out that twisting of space, whenever the twisting is strong enough, it actually will cause a twisting of time in a loop. I wrote two different papers. One, the first paper that I did, at least when I said this was solving Einstein, was to show that the circulating beam of ring laser, okay, would cause a twisting of space. And then what I had to do is I said, well, now if I up that, it turns out that what I did was I used the simplified forms of Einstein's gravitational field equation. Now, if you up the energy, it turns out that twisting of space can lead to a twisting of time. That was the second paper. But here's the kicker. With the twisting of space, which occurs at any level, okay, the energies there are not really that great, okay? They're actually within our technological bound. But now, to increase that energy to cause the twisting of time, it turns out that that's galactic. I mean, we're talking about energies that are, you know, okay.
Right. We're building a Kugel
unbelievable, okay. So that's the problem. So the thing is that, so literally my work splits into two portions. The one was showing that the circulating beam of light. And what I'm trying to do is to get the funding for just that portion of it, because if we see that, we know the basis for it. You know, mathematicians have a phrase, necessary and sufficient conditions, okay? If the twisting of space is a necessary condition, but it's not sufficient, okay? If we don't see the twisting of space at even those lower energies, we can go home. But if we do, then we might have. Now, here's the other thing that's missing in what I'm doing. Quantum mechanics. I have not taken into account what happens with quantum mechanics in this. Quantum mechanics may, in fact, impact this. It may make it more difficult, but it may simplify it. Now, why do I say it? The thing is that let's just go back to the basic equation that every school child knows, equals mc squared. Even Einstein, when he first came out with that equation, engineers that approached him, they said, can that practically be, you know, done? He wasn't sure that it could be, you know, used in a practical way to create energy, you know, even from a little bit of mass. It's quantum mechanics that led to that. And what I mean by specifically by that, the whole notion of fusion, okay, the whole notion of the whole notion of fission, right? In the first case, the whole notion of fission and the chain reaction, all of these things are part of quantum mechanics. And all of these things, you might say, overcome that barrier that would have been a problem otherwise, okay?
So at this point, I'm sort of imagining some kind of maybe satellite to keep it away from Earth's gravity. You're running a laser inside your satellite at whatever energies and whatever tight radius is required, and you are attempting to detect some kind of curving, some kind of, I guess, like frame dragging of space within the apparatus, which then could be used as an indirect detection of time dragging.
Right. As a matter of fact, I mean, you know, in fact, the even at the lower level, the gravitational field that's being created by the ring laser would actually allow time travel to the future. That's sometimes forgotten, okay, because that's twisting space. That's actually creating a gravitational field, and that in itself will cause time to slow down. I mean, time to bend.
Yeah. But I mean,
And
time
that
traveling
was-
into the future, that's no big deal. I do that all the time.
Right.
So,
Well, not quite the way in which they do it in the movies, or the way that
Yeah.
we'd like to do it, in which we could actually just go and spend, a couple of years in space and come back to the Earth, in decades,
Yeah.
which is something that happened in the movie Planet of the Apes. So, so we can't, when you say that, no, actually we can't do it easily. The only large-scale experiment with human beings that was done was an experiment that was done in 1971, which a lot of people still don't know about. It was an experiment that was done at the Naval Observatory, in which they took 2 atomic clocks. One of the atomic clocks was kept at rest at the Naval Observatory, and the other clock was put on an ordinary passenger jet. Okay, and they were able to demonstrate that the passenger jet flying at the speed of sound actually would cause time to slow down. However, it was only measurable with atomic clocks.
yeah.
Excuse me. The thing is that you would have to be traveling close to the speed of light to get it to go a little bit faster than that.
Yeah.
I mean, to go far in the future.
Yeah,
But
and
now-
I know that experiment has been replicated as well with, say, the International Space Station. They put really fancy atomic clocks on the space station. But
Right,
I want to
that's
go
it.
back. I want to go back to this potential experimental apparatus. Like, when you're
Well,
saying
the
that you're
thing is
looking for
you don't have
funding.
to, right. No, the thing is that you don't have to actually even go into space. It's a very, very simple equation that I arrived at, okay, at the end of which is always satisfying, because the equations themselves, solving them, I was not sure where it was going to go. But it turns out that there's a very simple equation. It actually says that there's a term in there. It's actually, you might say, it's the twisting of space. It's if for instance, suppose that I have this ring laser, and I put a neutron in there. A neutron spins like a little top, okay, and has an arrow, might say, along the axis of spin. And if I put a neutron in there, what I would find is that when you turn on the circulating light, this space in there would get twisted, and it would actually twist the neutron's spin.
Yeah.
It would actually cause the neutron spin to precess. The equation I came up with simply says that the precession is directly proportional to the intensity of the light, which you would expect. Okay, the greater the light energy, okay, the greater the precession. But here's the interesting thing: that's in the numerator. In the denominator, it turns out is the size of the ring laser. So what does that tell you? That tells you that the smaller I make the area, the greater the precession is. So contrary to what you might think, it says that what I would like to have is much energy as I can in as small an area as I can. This puts it within laboratory dimensions. So my prediction and the experiments are actually laboratory scale.
Perfect.
You just have to have a system in which you would do that. You could do that. And if we see that, then that would be the first test that this actually would allow us to have a laser-driven time machine. Eventually.
Right. And so in your perfect way, you mentioned, to actually make a direct detection of the time shifting, you would require, as you say, galactic levels of energy.
Right.
I'm sort of imagining you building your own Kugelblitz in the laboratory that then proceeds to suck out the entire planet Earth. But what would, practically speaking, if you could sort of carry,
how would you know?
Well,
Right.
no, yeah, I mean, practically speaking, if you could carry all the way out to the end of your research, that where the engineer mind would take over and say, how can I use this?
Yeah.
What would you see this kind of turning into ideally?
Well, for me, I mean, I have never been, to me, trying to send people back to that's great for science fiction. To me, what's more important is information. We're the information age. And I was always focused on what if I could send information back to the past, okay? And for me, it would be sort of like an early warning system. For instance, imagine if we could send information back to ourselves about tsunamis, earthquakes, okay, pandemics,
Yeah.
the thousands of lives that we could save millions of lives that we might be able to save. Okay. The thing is that, so that to me is one of the most important aspects of this, is the fact that we could send information back to them. And I can't tell you, Fraser, how many emails I get every single week from people saying, my son was in a car accident. Yeah. Is there any way that I can send? They don't say, can you send me back? They say, can I send him back a message?
Yeah, a text message. Yeah.
Right. You know?
Yeah.
Or someone was murdered. I mean, I've gotten, some of it is heartbreaking.
Oh yeah, I'm sure.
Okay? But the thing is that, so to me, being able to send information back is more important. Now, what form would this information take? Well, one of the things that I've conjectured is that, remember I was talking about neutrons. Now, subatomic particles, when we talk about spin, they can only spin in two different directions, a spin up and a spin down. That's it. There's no like in between. Mm-hmm. And suppose that I assign a 1 to the spin up and I assign it a 0 to the spin down. And suppose I have a stream of neutrons in which I have spin up, spin up, spin up, spin down. That's a 1, 1, 0. What are we talking about? Binary code. So by using the spin of subatomic particles, we could actually have information transferred that way. And that could be used in a detector that was. Now, here's the thing. You have to have a detector that would be able to get this information too. So a lot of people think that if you turn the time machine on, all of a sudden you're going to get stuff from the future. No, it isn't going to happen that way. You have to have something that's going to be able to be detected. It's like you don't hear the radio waves that are coming through you, you know?
Yeah.
But that's the point. So for me, that's the, you might say, the practical side of it.
And so I guess as with the black hole example, the limit, of course, is that you can only receive messages from when you turn the machine on and into the future.
That's right. In other words, let's suppose that I had this device and I turned it on today. And let's suppose I left it on for 10 years. Then someone 10 years from now could send back information 5 years, 7 years, all the way back up to the point. But before the device was turned on, that's the thing that's causing this twisting of space and time. It can't go any earlier than that. And that, as I said, that's a limitation that happens with black holes, with wormholes, and with my work.
But, one doesn't require you flying your spaceship close to a extreme, black hole with potentially millions of times the mass of the sun and all of the ramifications. Right. So I do like the one in the lab that, beep boops out data from the future every now and then. That sounds very convenient to me. Well, Ronald, it was a pleasure to talk to you. You've got a book that sort of goes into this in more detail.
Yeah, in more detail. And I should mention the book talks about how I became interested in this.
Here, actually, the book wasn't in frame, so I want to give you a better shot to grab the book and hold it right up there. There we go. Yeah, Time Traveler.
Yeah, it's called Time Traveler, and it actually is a memoir, really, with the science in it, because it talks about why I became interested in it. Actually, which had to do with the death of my father. So that was why that was the root of my becoming interested in it. It was a long, long path after that. But eventually I found out that Einstein was going to be I should say the thing that started me off really as a child. My father died when he was 33 and I was 10.
Yeah.
This is actually the
of course.
magazine. When I was 11, this is what saved me from actually going into a deep, deep depression, because when I read it, and I read in particular, it said, scientific people know very well that time is just a kind of space, and we can move forward and backward in time just as we can in space. As I said, I was 11 years old a year after my father died. And when I read that, that was the thing that opened up for me, because I thought if I could build a time machine, I could go back and see him again. What I realized ultimately was the key word in there is that scientists know very well. So I knew I was going to have to become a scientist.
Yes.
And that's what led me eventually to become a theoretical physicist in Einstein's work. And as I said, I go into all of that, as well as talking about black holes and wormholes and other things in my book.
Absolutely fascinating. And so if people want to, obviously people can pick up the book. If they want to find out more about your work and what you're working on, where should they go?
Well, actually, I'm on Facebook, and I actually have podcasts. Yours will be one of them.
Oh, great.
There.
Okay.
And so what I would suggest is that people actually contact me on Facebook. They can go to my university website, but I don't update it the way that I do
Right.
on my Facebook. And my Facebook is devoted towards the sciences.
Right.
So that's what I would suggest, is to contact me on Facebook. Be happy to add people as a friend, and that would keep them up to date on what I'm doing.
Especially Congress people looking to fund new science experiments now that the Large Hadron Collider, needs a follow-up replacement. So,
yeah. I should mention, incidentally, the book, which is available on Amazon, by the way, that Hollywood has had some interest in it. So keep your eye out on that.
That sounds great. I look forward to binging it on Netflix. All right. Well, Dr. Mallett, thank you so much for taking the time to chat with us today. Good luck. But I guess you would already know from the future. Anyway, we won't go into the paradoxes, but thanks a lot. Take care.
All right. Thank you very much. Bye-bye.